I'm Bob Warfield from CNC Cookbook. Today I want to talk about micromachining and specifically about the #1 issue impacting tool life when micromachining. What is micromachining exactly? There are a lot of different definitions, but the one I like is this one I've shown here. Micromachining is any machining you do with cutters smaller than 15 thousandths of an inch in diameter. When your cutters are that small, part features can be 1,000th of an inch or less, and tolerances are measured in tenths or microns. This is very demanding work. We see micromachining used for all sorts of applications like microfluidics, microwaves, fiber optics, medical devices, semiconductors, and other electronics applications. What brings them all together is that each of these applications has requirements for very small features that must be machined to tight tolerances. Since the work is so challenging, this can be a very profitable niche for a shop that has the expertise. The problem is, micromachining expertise is hard to come by because it isn't just standard machining work. Starting at about 100 thousandths diameter tools and smaller, the cutting physics actually start to change versus conventional machining. Things quit working the way you expect. There are a whole host of differences, but some of the most important include it's impossible to make your edges sharp enough at these scales. It's hard to impossible to create positive rake geometries on cutters. This means that rubbing is very common, and that drives up the temperatures and makes cutting forces at least 2 times higher than conventional machining models predict. On top of all that, the tiny little tools used for micromachining can be exceptionally delicate. Rigidity is a function of diameter to the 4th power, so the impact of much smaller diameters on tool strength and rigidity is magnified enormously. That's why tool life is always the big challenge for micromachining work. The #1 tool life issue when micromachining is runout. It's not the only issue by any stretch, but it's the one to look at first. Runout is any error that causes the tool's cutting edges not to be properly aligned with the spindle's axis. Let's take a closer look at how this affects your tool. Here I'm showing 2 4-flute end mills viewed from above and looking straight down the spindle axis, which is that blue circle you see. The tool on the left has its cutting edges perfectly aligned with the spindle axis, so it has no runout. But look closely at the tool on the right. It's off axis by about 10% of the tool's diameter. It's shifted just to the right, this way in other words. You can see clearly what happens with this level of runout. The tooth on the right has huge chip load. It's taking a much bigger bite out of the material. The tooth on the left is hardly engaging the material at all, and so it's not doing any work. The remaining top and bottom teeth are taking very light cuts. The tooth at the right is having to do most of the work in the cut. So one way to think about runout is that the true worst case chip load of a tooth is equal to the chip load dictated by feeds and speeds plus the runout plus any tool deflection of the tool in the cut. And remember, these tools are less rigid. Deflection is also a fact of life. What are the sources of runout? Well, there are 3, and I've tried to give you an idea here of their relative magnitude. First, the spindle itself is always going to have a little bit of runout, hopefully a very little. It should be on the order of about 2/10 or less. Second, the tool holder and any collets will contribute some runout. Typically 4 thousandths or so for a high quality ER collet. And lastly, the tool may not be ground quite true, and so we might see another 2/10 from that inaccuracy in the tool grind. All told, we're looking at something on the order of 8/10 plus or minus for a typical micromachining application. Our goal is to keep this stack up of runout errors to less than 10% of cutter diameter in order for the impact of runout on your tool's life to be minimized. So how can we reduce runout? Start by realizing that measuring runout on tiny little tools is difficult. You can't just clock them with your DTI like you would larger cutters. Lasers or capacitive resistance sensors are called for, and shops typically will bring in a specialist to make these measurements if they suspect they're having runout problems. Aside from the measurements, look for newer machines and spindles. Fresh bearings will keep things tighter. Higher RPM spindles typically are built to better tolerances and will also have lower runout in most cases. Use high quality tooling to minimize the runout errors from the tool grind. Now, as we saw, the biggest source of runout and one of the most easily improved comes from your tool holders. Make sure you're using high quality tool holders for starters. That almost goes without saying for this kind of work, but the type of holder matters a lot too. Typical ER collet systems can get down to about 4/10 of runout. That means if everything is working out perfectly, how often does that happen? You can run them with tooling down to about 8 thousandths in diameter. To do better, you'll need to go to UP collets or even an ultra precision collet system that was purpose made for micromachining applications. By using these higher performance tool holding solutions, you can really cut down on the runout, which in turn will really improve your tool life when micromachining. Thanks for listening, and I'll see you again on our next CNC Chef video.